Welcome to the lecture series on deep learning in artificial neural networks. This video compares deep networks with shallow networks. In the previous video, I explained the hypothesis that hyperplanes might play a role. Now let's look at the regions that are carved out by hyperplanes. Let's start in 0 dimensions. Well, 0 dimensions means I just have a point. How many regions are there? Well, 1. Now let's look at 1 dimensions. So this is the input space. And if I have 0 hyperplanes, then I have 1 region. With 1 hyperplane, I have 2 regions. With 2, I have 3. With 3, I have 4. With 4, I have 5. So I have in total n regions plus the one from before, the one from 0 dimensions. Now let's go from 1 dimensions to 2 dimensions. So this is my first dimension, and the hyperplanes are now projected into 2 dimensions. This is the second dimension, and they are now just parallel hyperplanes. But I now take the first hyperplane and I exploit the second dimension and tilt it. And then I create a new crossing, which means I also create a new region. If I tilt further, I will create 2 further regions. Thus, for each crossing, I create a new region, and now we are going to count these regions. So I had n hyperplanes. I turned one of these hyperplanes, and when I turned it, I created n-1 new regions. I could turn each of the n hyperplanes and count the regions, but then I overcount by a factor of 2. So these are the extra regions that I create in 2 dimensions. In 1 dimension, I had already n regions, and in 0 dimensions, I had already 1 region. Now let's go and continue this sort of induction steps and go to 3 dimensions. In 3 dimensions, I have now my hyperplanes, and they are for the moment vertically. And so if I look at these hyperplanes from the top, if I take the bird's eye view, then it would just look like my 2D picture before. But now I can start and tilt one of the hyperplanes. And if I do this, I create new regions each time it goes over one of the crossings. And this now continues to this final formula. And the upshot of all this is that the total number of regions cut out by n hyperplanes in a d-dimensional space has this combinatorial factor, and this is the sum up to the d dimensions. You remember that I started in 0 dimensions, then in 1, then in 2, and so we go up to d dimensions. Now this factor can be approximated by this n to the power of d divided by d factorial. So first point, there are many regions carved out in d-dimensional space. Now, second point, these regions should not be labeled with arbitrary targets unless we have additional layers, because just remember the XOR problem, even for a single configuration like this, assigning labels in that form here makes it difficult. You have to take an extra layer to resolve this classification task. So there are many regions, but there seems to be, in real-world problems, a strong prior that we do not need arbitrary labeling of these regions, so that with a polynomial number of hidden neurons, we get good generalization. So this is one potential explanation. This is one hypothesis. that could explain or illustrate why it's good to have several layers of classification, maybe in addition to a couple of pre-processing layers that do, for example, for imaging some convolutional steps. And so here's an illustration of this. We cannot assign arbitrary labels for each of the many subregions, but some labels will then be automatically assigned, for example, for a region down here, which doesn't have any data yet. Now compare this with a nearest neighbor classifier. A nearest neighbor classifier in this region would automatically assign the red type label on this side and the brownish type label on the other side. Whereas here we can transport, with these hyperplanes, we can transport some specific labels for the whole region. So it's a different type of generalization compared to what a nearest neighbor algorithm would do. So this is just a hypothesis of an explanation, but we can really compare deep networks with shallow networks. And what we look at is the test accuracy, the generalization, the validation data. And as a function of layers, this increases. Okay, now what's the normalization? So let's look at the next slide. Here it's normalized to the number of parameters. The numbers are big. And now we can compare a 11-layer convolutional network, which is the red line up here, with neural networks that have a different structure, for example, fully connected, or a convolutional network with only 3 layers, but more neurons per layer. And you can compare that the network with more layers is effectively better. So somehow the prior structure of the deep network seems to match the structure of real-world problems we are interested in. And one hypothesis is that the network reuses features that are learned in other contexts. So if you think of a database that contains examples of a green car, a red car, a green bus, a red bus, tires, windows, lights, houses, well, then you can make new combinations. Maybe it can generalize to a red house, even though there was no example in the database containing a red house. So this is the end of this lecture series. We covered a lot of ground. I spent quite a bit of time on the error function landscape or loss landscape. And the main message is there are a huge number of equivalent minima and even more saddle points. Then we looked at ways to increase the gradient descent speed towards one of the minima. And momentum is nice because it gives a faster effective learning rate in boring directions, and it slows down in directions where it would oscillate otherwise. So effectively, it suppresses oscillations. On top of this, an algorithm such as Adam gives a faster effective learning rate in low noise directions. And the noise here is meant in the sense of mini batches or stochastic gradient descent. And now we have the no free lunch theorem that says no algorithm is better than others. Nevertheless, deep networks perform well. So they are better than shallow ones on real-world problems. And this might be due to feature sharing or to other properties. In the specific example of images, the convolutional structure that guarantees translation invariant is super important.